A Nobel Prize-winning physicist looked at his own data and said 3 words that should have shaken every science classroom on Earth. We have misunderstood the universe. Not a grad student, not a fringe theorist posting on Reddit at 2 a.m. Adam Riess, Johns Hopkins University, the man who helped discover that the universe is accelerating, a finding so significant it won him the Nobel Prize in Physics. And he wasn't being poetic. He wasn't being humble. He was reading numbers off a page and telling you plainly that something in our model of reality doesn't add up. Here's what makes this terrifying. The model he's talking about has worked flawlessly for nearly a century, predicted the Big Bang. It explained the first elements. It mapped the large-scale structure of hundreds of billions of galaxies with almost supernatural precision. And now, the most powerful space telescope ever built. A machine so sensitive it can detect the heat of a bumblebee on the moon is pointing at the sky and returning data that the model cannot explain. This isn't a glitch. This isn't a rounding error. This is cosmology standing at the edge of everything it knows. The number that broke physics. Let's start with a number. 67. That's how fast the universe is expanding right now, according to one method. For every 3.26 million light-years you look outward into space, galaxies are flying away from us 67 kilometers per second faster. It's called the Hubble constant, named after Edwin Hubble, the astronomer who first proved the universe was expanding at all back in the 1920s. Now here's the problem. When you use a completely different method to measure that same number, you don't get 67. You get 73. 6 kilometers per second per megaparsec. That sounds small. It is not small. In a field where measurements are routinely precise to within 1%, an 8 to 9% gap between 2 independent methods isn't noise. It's a siren. It means either one of the measurements is wrong, or the universe is doing something our best equations weren't built to handle. To understand why this matters, you need to understand the 2 methods. The first looks backward, way backward. The European Space Agency's Planck satellite spent 4.5 years mapping the cosmic microwave background. Think of the CMB as the oldest photograph ever taken. A faint glow of radiation left over from when the universe was just 380,000 years old. A newborn, cosmically speaking, still too hot for atoms to exist. Planck mapped that glow with extraordinary detail. Physicists took that map, fed it into the Standard Model, and ran the equations forward nearly 14 billion years. The answer they got for today's expansion rate, 67. The second method doesn't model the past. It measures the present. Adam Riess and his team, a collaboration called SH0ES, built what astronomers call the cosmic distance ladder. They start close with pulsating stars called Cepheid variables. These stars breathe. They expand and contract on a rhythm, and that rhythm is directly tied to how luminous they truly are. Measure the pulse, calculate the true brightness, compare it to how bright the star looks from Earth, and you've got a precise distance. From there, the team steps outward to galaxies containing both Cepheids and a special class of exploding star, Type 1a supernovae. These explosions are nature's standard candles. They all detonate with roughly the same peak brightness. Once you calibrate them against Cepheids in nearby galaxies, you can spot them hundreds of millions of light-years away and calculate distances to their host galaxies with confidence. Combine those distances with how fast the galaxies are receding, and you get the Hubble constant. Riess's answer, 73. For years, the assumption was that someone had made a mistake. The most popular suspect was stellar crowding. Cepheids live in the dense, dusty disks of young galaxies, and older telescopes sometimes blended their light with neighboring stars, making them appear brighter than they actually were. Brighter Cepheids mean shorter calculated distances. Shorter distances mean a higher Hubble constant. Clean up the crowding, the argument went, and the tension disappears. So Riess did something decisive. He pointed the James Webb Space Telescope at those same stars. Webb orbits 1.5 million kilometers from Earth, beyond the thermal interference of our atmosphere. Its 6.5-meter gold-plated mirror collects infrared light with a sensitivity that makes Hubble look like a disposable camera. If blending was the culprit, Webb would expose it. The Cepheids would look dimmer. The distances would stretch. The Hubble constant would slide back down towards 67 and the crisis would be over. The data came in. The Cepheids looked exactly the same. The distances held. The expansion rate stayed at 73, confirmed now across 1,000 Cepheids, 5 host galaxies, 8 supernovae, stretching all the way out 130 million light-years to a galaxy called NGC 5468. In early 2024, the SH0ES team published their conclusion in the Astrophysical Journal Letters. Measurement error, meaning nearly every available atom in their surrounding dark matter halos had converted into stars. In a normal universe, that conversion rate sits around 10%. The rest of the gas gets too hot, gets blasted away by radiation, or simply never collapses. These galaxies appeared to have no waste. Physics doesn't work that way. Not in any model anyone had constructed. Then came a partial correction. Catherine Sharwater, a graduate student at the University of Texas, led a study in mid-2024 that re-examined the data and found something crucial. Many of these apparently monstrous galaxies were being inflated by their own black holes. These objects, nicknamed little red dots for their compact size and infrared color, hosted voraciously feeding black holes at their centers. The friction from all that infalling gas heated it to extreme temperatures, radiating enormous amounts of light that blended seamlessly with the galaxy's starlight. Sharwater's advisor, Stephen Finkelstein, was direct about it. There is no crisis in the standard cosmological model, not from the galaxies at least. But here is where the story refuses to close neatly. Even after removing every little red dot, roughly twice as many massive galaxies remained in the early universe as the standard model expects. Not enough to shatter the model, enough to strain it. Churovsky herself suggested that star formation may simply have been faster in the denser, richer conditions of the early universe. A reasonable explanation, but one that requires the model to flex in ways it was never designed to flex. And then in early 2025, Webb found something that had no easy explanation at all. A massive spiral galaxy, quickly nicknamed the Big Wheel, sitting in the first 2 billion years of cosmic history. Spiral structure is not something that assembles quickly. It requires orderly, calm, sustained growth over billions of years. It requires a galaxy that has mostly stopped colliding and merging and has settled into a stable rotating disk. Finding one this ancient was, according to Themia Naniakara of Swinburne University of Technology, either evidence of an unusually tidy assembly process or proof that most of its stars formed in place, without the violent collisions that standard models require to build galaxies this large. The early universe, it turns out, was not the simple, chaotic nursery we assumed it was. The scaffolding is shaking. Every model of the universe rests on a foundation. And cosmology's foundation has a name: cold dark matter. You cannot see it. You cannot touch it. No detector on Earth has directly measured a single particle of it. And yet it makes up roughly 27% of everything that exists. It is the invisible scaffolding around which visible matter, stars, planets, gas, every galaxy you've ever seen in a photograph, is draped like decoration on a frame. The cold dark matter model isn't just one ingredient in the standard cosmological recipe. It determines where galaxies form, how they cluster, how matter is distributed across the largest scales of the universe. Every prediction cosmology makes flows downstream from assumptions about what dark matter is and how it behaves. The cold in cold dark matter means these particles move slowly relative to the speed of light. That slowness matters enormously. Cold, sluggish particles clump together efficiently, building a specific pattern of cosmic structure. Dense filaments connecting galaxy clusters, with vast empty voids in between. This pattern has been mapped across hundreds of millions of light-years, and it matches the Standard Model's predictions remarkably well. Until, potentially, it doesn't. A study published in Nature Astronomy in late 2025, led by Alvaro Pozo and including researchers from MIT, Harvard, and Taipei, examined the shapes of young galaxies observed by Webb and found something unexpected. Many of them were elongated, stretched out, cigar-shaped, prolate forms that don't match what cold dark matter predicts for young galaxy structure. They do, however, match predictions from alternative models. Warm dark matter, wave dark matter. These are frameworks in which dark matter particles are lighter and move faster, or in which dark matter behaves less like a particle and more like a quantum wave spread across space. In these models, the large-scale filaments of cosmic structure are smoother, and gas flows along them in elongated streams, naturally producing the stretched, cigar-shaped galaxies Webb is finding. This matters in ways that ripple outward through every corner of the field. If dark matter particles are lighter or behave differently than the cold model assumes, it doesn't just affect galaxy shapes. It shifts the expected distribution of dwarf galaxies orbiting larger ones. A distribution that has already been a source of ongoing tension for years. It changes how gravitational lensing bends light around massive objects. It alters the predicted mass of galaxy clusters. You cannot swap out the foundation of a building and expect the walls to stay where they are. There is also a second, quieter tension that has been accumulating in the background, the S8 tension. The Standard Model makes a specific prediction about how clumpy matter should be, how tightly it clusters across space. When astronomers measure that clumpiness directly, they consistently find slightly less of it than the model predicts. Adam Riess has called it the little sibling of the Hubble tension. Less dramatic, less discussed, but persistent. And if both tensions turn out to be real and related, they may not be two separate problems. They may be two symptoms of a single, deeper flaw, two cracks running through the same wall. Dark energy adds its own layer of uncertainty. It makes up roughly 68% of the total energy content of the universe. It is responsible for the accelerating expansion that Riess himself helped discover in 1998. And despite being the dominant component of everything that exists, it remains entirely unexplained. Dark energy is not a description. It is a placeholder, a name physicists gave to something they cannot identify, cannot measure directly, and cannot explain with any theory they currently possess. The Standard Model does not tell you what dark energy is. It tells you how much of it there is. That is a significant difference. The edge of the map. Here is what the Standard Model has right, and it is worth saying clearly before anything else. It predicted the abundances of hydrogen, helium, and lithium produced in the first few minutes after the Big Bang, and observations confirmed those predictions to extraordinary precision. It explained the pattern of temperature fluctuations in the cosmic microwave background, a map of density variations from 380,000 years after the universe began, and that explanation matches the data so perfectly it is almost unsettling. It accounts for how galaxies cluster across billions of light-years in a pattern so specific that getting it wrong by a small margin would cascade into obvious failures everywhere. No competing model comes close to this track record. The Standard Model is not wrong. It is incomplete. And that distinction is everything. Cosmology has been here before. In the 1990s, measurements of the oldest stars in the universe suggested they were older than the universe itself. Older than the thing they lived inside. Logically impossible. And yet the data was clean, the measurements were careful, and the contradiction refused to disappear. It looked, for a period, like a fatal flaw at the heart of the entire framework. Then in 1998, two independent teams, one of them led by Riess, discovered that the expansion of the universe wasn't slowing down. It was speeding up. Something was pushing everything apart with increasing force. They called it dark energy, and its existence changed the calculated age of the universe just enough to make it older than its oldest stars again. What looked like a death sentence was actually a missing piece. The crisis didn't end cosmology. It expanded it. That pattern is what makes this moment feel significant rather than catastrophic. New instruments are arriving. NASA's Nancy Grace Roman Space Telescope will conduct wide-field surveys specifically designed to probe dark energy at scales Webb cannot reach. The European Space Agency's Euclid mission is already mapping the geometry of the universe across billions of light-years, the most ambitious survey of cosmic structure ever attempted. Future data releases from the Gaia Space Telescope will allow astronomers to calibrate Cepheid distances using pure geometry, removing an entire category of potential systematic error from the distance ladder. The Atacama Cosmology Telescope has produced the most detailed ground-based map of the cosmic microwave background ever made, and its latest results have nudged the Planck estimate of the Hubble constant slightly upward, though not yet far enough to close the gap. Something is out there in those 14 billion years we've never directly observed. Some ingredient we haven't identified, some process we haven't modeled, some property of spacetime we haven't yet imagined. That is not a failure. It is precisely what science looks like from the inside when it is working. A species on a small rocky planet, orbiting an unremarkable star in the suburbs of a mid-sized galaxy, using mirrors and mathematics to argue about whether reality is expanding 6% faster than it should be, and getting genuinely, productively upset about it. The universe isn't broken. Our map of it is just incomplete. And the next version, whenever it arrives, built on whatever discovery closes these gaps, is going to be stranger and more beautiful than anything we've drawn so far.